In this video, we're going to talk about implicit differentiation and related rates. Objectives will be to find derivatives using implicit differentiation, to find second derivatives using implicit differentiation, to use implicit differentiation to find slopes of curves at given points, to use implicit differentiation along with product quotient and chain rules, to find derivatives of functions, to solve applications involving related rates, and to solve related rate problems using geometry. So let's go ahead and get started. First, recall the definition of a function. Y equals f of x, where y is the dependent variable and x is the independent variable. Meaning that the variable y depends on the value that we choose for x, but we make an independent choice there for x. We choose x, y depends on it. So there's exactly one y value for each x value. Output, input, if you want to think of it that way. Every input has exactly one output. This is an explicitly defined function of x called f, which defines y. It's explicit because we get y all by itself on the left-hand side, and everything that's not y, the constants and x's, are on the right-hand side. So what about something like a circle? We can't get all of the y's apart from the x's here. We can try, but if we rewrite this expression, we get something like y squared is equal to r squared minus x squared. And then when we take the square root, y equals plus or minus the square root of r squared minus x squared. And that's not a function. Or we could try to make x a function of y. Say x squared equals r squared minus y squared, and x equals plus or minus square root of r squared minus y squared, and it doesn't work either way. We are stuck here. So we actually would have to graph two separate functions here. And I'm just going to look at the make a green color here for the minus so that you see the top part is going to be in blue, is going to go from negative r to r through r is up here. And hopefully I can draw something that looks like a circle here. So that should be the top half of the circle. And then I have the bottom half of that circle that I'm going to draw in green. It's going to be like so. It's going to go through negative r down here. And I'm not really great at drawing these, but y equals negative square root of 1 minus of r squared minus x squared. And this top one is y equals the positive square root of r squared minus x squared. So can we always come to the conclusion that we can write two explicit functions of x and look at each piece individually if we wanted to find slopes up here and slopes down here? Could we do that? No, it's not always possible. No, it's not always possible to write two explicit functions of x. So for example, we could have implicitly defined functions like y squared ln of y plus ln of x is equal to x squared plus 2x minus 9. You can't solve for x, you can't solve for y there. So what are your options for finding an expression for the derivative? Option 1 would be what we did to solve for multiple explicit functions like this, and then differentiate both of them and see what happens. So in this case, we have y equals the square root of, let's call this 1 on the right-hand side. So this is going to be 1 minus x squared. And second function is going to be y equals negative square root of 1 minus x squared. So when we differentiate, we get y prime equals 1 over 2 root 1 minus x squared times the derivative of the inside is a negative 2x. So that becomes a negative x over root 1 minus x squared. And y prime here is a negative 1/2 root x squared times a negative 2x. Negative negative is a positive. Y prime is going to be x over root 1 minus x squared. Okay, so in general, this would come out to be y prime is going to be a negative x over y. Is how that's going to work out, because when y was negative, this was positive. When y was positive, this was negative. So how can we use implicit differentiation? We can treat y as a function of x and differentiate implicitly. So that's how you would say what I'm about to do. So let me just show you how I would do that. So if we have x squared plus y squared is equal to 1, and we take the derivative with respect to x of x squared plus the derivative with respect to x of y squared is equal to the derivative with respect to x of 1. Derivative with respect to x of x squared, that's 2x. Derivative with respect to y, or squared, we're going to use the chain rule because y is a function of x. Assume y is a function of x unless you know otherwise. We have 2y times the derivative of the inner function y is dy dx. Derivative of a constant is 0. So 2y dy dx. Solving for the dy dx term is what I'm doing here. Divide both sides by 2y. 2 divided by 2. So dy dx is equal to negative x over y. And that's what we said that we thought that we saw up here for our pattern. And that is what the implicit derivative is here. So negative x over y is what dy dx is. So let's look more exactly at what happened with the second term. When I took the derivative with respect to x of y squared, I got 2 times y times, and you can call this dy dx, or you could call it 2 times y prime. You'll see in some later examples here why I like the dy dx notation as opposed to the y prime notation when we get to something called related rates that we're about to talk about. So what if y equals x squared plus 4? You know that you would take the derivative of each piece like this, and the derivative with respect to x of x squared would just be 2x, right? So in this case, though, we're going to use the chain rule because we took the derivative of the outer function, which was the squaring function, like we just did here, 2 times that inner function, and then we have to take the derivative of the inner function. So implicit differentiation is just the chain rule in disguise. We don't see the inner function because we replace it with our dependent variable. Okay. As we can see, there's chain rule happening behind the scenes. This is what happens with all of the rules that have a chain rule. So, and we already did this here, but I'll do it again. This is 2x plus 2y times y prime is equal to 0. 2y, y prime is a negative 2x. Y prime equals negative 2x over 2y. So y prime is a negative x over y, just like we saw before. So this is the idea that y is our inner function g, and the derivative with respect to x of g of x squared is 2 times g of x times g prime of x, and just the y's are the g of x's here, so this is 2y times y prime. All right. We can use the product and quotient rules with implicit differentiation here. For example, if I have xy is equal to 2, my u is equal to x, my v is equal to y, my u prime is equal to 1, my v prime is equal to y prime. So on the left-hand side, when I write my product rule, u prime v plus v prime u, derivative of a constant is 0. Let's solve for y prime. Y equals x, y plus x times y prime is equal to 0. X times y prime is equal to negative y. Y prime is equal to negative y over x. So that's an example of implicit differentiation that required the product rule. The product rule is occurring with the derivative of xy, that specific term. Now let's look at this example. We take the derivative with respect to x of both sides. I get 3x squared plus 2y times y prime minus 1 times y minus x times y prime is equal to 0. Just taking the derivative of the first part, leaving the second part alone, then adding, which means keep the sign here, of derivative of the second part, leaving the first part alone. So 3x squared plus 2y y prime minus y minus x y prime is equal to 0. Let's move my terms that don't have y prime to the other side. 2y y prime minus xy prime is equal to a negative 3x squared plus y. Now I'm going to factor out my y prime and get 2y minus x. So y prime is going to be negative 3x squared plus y divided by 2y minus x. Or we can write that as y minus 3x squared over 2y minus x. All right, let's implicitly differentiate both sides here. That side is 0. 2y y prime plus derivative of the first part, leaving the second part alone, plus derivative of the second part, leaving the first part alone. And move my terms without y prime in them over to the other side by subtraction. Factor out my y prime. Divide by the part that's not y prime. Use implicit differentiation to find y prime. So let's use some rules here from pre-calculus first, that a product inside of a log can be made to a sum of logs. Now I can deal with this derivative explicitly and this derivative implicitly. And that's 0. 1 over y times y prime is equal to a negative 1 over x. Multiply both sides by y. Y prime is a negative y over x. Now let's find the slope of the tangent to the graph of a circle with a radius of 3 at these various points. So we have x squared plus y squared equals 3 squared, or x squared plus y squared is equal to 9, assuming that we're centered at 0, 0, because it didn't tell us otherwise. So we have 2x plus 2y times y prime is equal to 0. 2y times y prime is equal to negative 2x. Y prime is a negative 2x over 2y, which is a negative x over y. So at the point square root of 5, 2, y prime is equal to a negative root 5 over 2. At the point negative root 5, negative 2, y prime is going to be a negative, negative is a positive, over a negative, that's negative root 5 over 2. at root 5, -2. Y prime is going to be the opposite of x divided by y, and negative divided by a negative is a positive. You'll see that there's multiple places with the same slope here. If you're at opposite sides of the circle there, your tangent lines will have the same slope if you're reflecting across the origin. So you can differentiate implicitly to find a derivative of higher order, higher than the first order. You're just going to have to go back and make some substitutions when you do that with your first derivative that you've already found. So find your first derivative to be dy dx. Then d2y dx2 will be your second derivative, y double prime, and that's the derivative with respect to x of your first derivative. Third derivative is d3y dx3. This should be a 3. And that's just the derivative of the second derivative. So that's the third derivative. So let's find the second derivative for the example that we had before. ln of x plus y, I'm sorry, ln of x times y is equal to 6. And we said that that's the same thing as ln of x plus ln of y is equal to 6. So we had 1 over x plus y prime over y is equal to 0. Y prime over y is equal to -1 over x, and y prime is equal to -y over x. Second derivative, we want to use the quotient rule. So the derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared. So y double prime is going to be a negative, and then y prime was a -y over x times x. And then this is going to be plus, so this was a negative and a negative, y over x squared. So this is going to be y plus y is 2y over x squared. All right, so always try and get this as simple as possible. Don't leave y primes in there if you can help it. Get everything back to x and y so that if you're given an ordered pair, you can make a substitution and get your nth derivative there. So now let's go ahead and talk about why we care about this. We get things that are called related rates. So consider the flow of blood through a blood vessel. F is the blood flow, K is a constant, R is the radius of the vessel here. So we would say something like F is directly proportional to R to the fourth, something like that. And K is that constant of proportionality. So everything is changing over time. So that's the big idea here, is that everything is changing with respect to time, though we don't see t as an explicit variable. We don't see our function explicitly defined in terms of t. Okay, so we have really, we have f of t, the blood flow is a function of time, and we have r of t. So really what we have is f of t is equal to k times r of t raised to the fourth power. So that lets us differentiate with respect to t and find df dt and dr dt. And then our question is, are they related in some way to each other? That these are called rates of change. And are these rates of change related? If so, they are what we call related rates. So let's see if we can take this original equation, differentiate both sides implicitly with respect to t, and see if we can find a relation there that relates df dt to dr dt. So differentiating with respect to t implicitly, I get df dt on the left. K is a constant that just sits there. Df dt is equal to k times 4r to the third. Using the chain rule, we get dr dt here. So df dt is equal to 4k r cubed times dr dt. So can we measure f, r, df dt, and or dr dt in real life? Yes, we can. So all of those things, we could get 3 of the 4 things and find the fourth if we knew this constant k. If we knew all 4 of these things, 1, 2, 3, we actually would need to know f in this case for this related rate. If we knew these 3 variables right here, we could solve for the constant k that's related to that particular blood vessel for that person. So yes, we can actually do that. Now think of another example like the height of a tree and the radius of the trunk. So we might have an equation that looks like h equals 15r to the 2/3. That as the radius of the trunk, it gets bigger, that the height of the tree should be bigger because the tree is older. So then we could differentiate both sides with respect to t and get 15 times 2/3 r to the 2/3 minus 1 times dr dt. 3 goes into 15 5 times. dh dt is equal to 5 times 2 is 10. R to the negative 1/3 times dr dt. So there's my related rate equation. If I were given information such as dr dt was equal to 3/4 of an inch per year, and r at the moment of time I was looking at the tree was 8 inches, could I find dh dt? I absolutely could. It would be 10 times 8 to the negative 1/3 times 3/4. So this is 10 divided by the cube root of 8 is 2 times 3/4. It's going to be 15/4 of an inch per year. As we were told in this problem that this is inches per year, right? So this will also be inches per year. So that's almost 4 inches per year. This is 3.75 inches per year is how quickly the tree is growing. When the radius of the trunk is changing by a rate of 3/4 of an inch per year, and R is equal to 8 inches. Now let's assume x and y are differentiable functions of t. Find dx dt given that x equals 5, y equals 12, and y dt is 2 for the function y squared minus x squared equals 119. So when we differentiate with respect to t, 2y dy dt minus 2x dx dt equals 0. So we have dx dt is what I'm trying to find. X is 5, y is 12, dy dt is 2, dx dt is unknown. So 2448 minus 10 dx dt, negative 10 dx dt is equal to a negative 48. Dx dt is equal to 48 over 10 is equal to 24 over 5. That's also the same thing as 4.8. All right. Now let's do an example with geometry here. A 15-foot ladder is resting against a wall. The bottom of the ladder is initially 10 feet away from the wall. And is pushed towards the wall with a rate of 1/4 foot per second. Since it's being pushed towards the wall, I'm losing this distance x. That's why this is negative. How fast is the top of the ladder moving? This should be a positive number since it's going up the wall when t equals 12 seconds. So we have the Pythagorean theorem, x squared plus y squared is equal to r squared. Squared plus y squared is equal to 225. 2x plus 2y dy dt. This is dx dt is equal to 0. 2y, let's see. So when t is 12 seconds, so 10 minus 1/4 times 12 is 10 minus 3 is 7. So we're actually looking at this being 7. And if that's 7, then I have 15 squared minus 7 squared is 225 minus 49. Which is 176. And so this side is square root of 176. It doesn't come out nice and pretty. Let's see, 176 is 2 times 88, which is 2 times 44, which is 2 times 22, which is 2 times 11. So that is 4 root 11. Okay. Now that I have that, I can try and find dy dt here. So 2 times x is 7, dx dt is -1/4, plus 2 times y is 4 root 11 times dy dt is equal to 0. So this is -7/2 plus 8 root 11 dy dt is equal to 0. Dy dt is going to be 7/2, and then 8 root 11 comes down here. So dy dt is going to be exactly 7/16 root 11. I don't like leaving that root in the denominator, so I'm going to rationalize. Dy dt, 7 root 11 over 16 times 11. 16 and 16 is 176. All right. So the latter is, I think if I approximate this, check it and see if this is right, but I think that it's 1319 feet per second here. So the ladder is moving up the wall at a rate of 0.1319 feet per second after 12 seconds from being pushed towards the wall. I did not do any business related problems here, but related rates are really important with marginal revenue, marginal cost, marginal profit. Those are all these ideas of related rates where time is changing usually. And you need to find dx dt, dc dt, dp dt, dr dt, those types of things. Sometimes we're taking the derivative with just respect to production, and that's explicit usually instead of implicit. But you will get these implicit derivatives with cost, revenue, and profit. So, all right. That's it for this video. We'll come back next time and talk more about applications of derivatives and try and use them to minimize and maximize functions. And like we will want to minimize cost, maximize revenue and profit, those sorts of things. So see you for the next video.